Okay. So
Okay, very good. Yes. All right. Sorry about the slight technical delay at my end. Thank you very much for coming. Thank you very much for inviting me to speak at this series. So I should say at the outset that I'm trying to do something experimental, a little bit different from how I might usually give a talk. As you can probably say, rather than using slides, I'm using a notebook. We'll see how it works out. There's one or two places in the talk where hopefully I can do something a little bit live so that it kind of replicates what one would do if I had a whiteboard or blackboard in front of me. Still though, quite a bit of this should be slide-like, but with some obvious differences. We're going to talk about how to color your enemy's graph. So, right, adversary's graph, opponent's graph. Let's not use this negative a word as enemy. So yeah, let's begin. Oh, I lost one page. Okay, all right. Yeah. Right, so this talk is about data streaming, and I guess I didn't ask what kind of audience I should pitch this talk towards, but I'm pitching it towards a general theory audience rather than a specialist in this particular topic. So hopefully that's okay. So I'm not planning to go very in-depth into any computations or proofs, but I should still be able to give you a high-level idea of several proofs. So I am going to assume that you've seen the streaming model before. It's so standard now that yeah, I think just about everybody in theory knows this. So in this talk, we're going to be talking about graph coloring. Once again, graph coloring is a problem that I think everybody knows. A quick reminder though, you have a graph, it's undirected, and there's n vertices in it. There's a palette from which you have to choose colors to assign to the vertices. And the important requirement is that no edge should be monochromatic. Yeah. Oh, just curious, is my pointer showing when I do that?
yes, it is.
A red pointer. Okay, good. Thank you. Now, you might know that graph coloring is a very hard problem. It's NP hard. It's much more than NP hard even. But this is the version where you have to color the graph with the minimum possible palette size. Now, that is not the version of graph coloring we're going to be looking at today. This is a much, in this sense, simpler version of graph coloring, where we say that the maximum degree of the graph is delta, and I just want to produce a delta plus 1 coloring. And this exists for almost trivial reasons, and the algorithm that gets you that is also just as trivial. It basically says pick colors greedily from your palette, and you'll never run out of colors because you have one more in your palette than there is degree. We could, I guess, demonstrate this with this particular graph. So for instance, I could say, make this guy. So here the maximum degree is 3, I believe, in this graph. So we're asking for a color with 4 colors, for coloring with 4 colors. So, I can use a color here, maybe the same color here, and then some other color, and say here, and maybe do something else here. So I want to get to a point where I'm actually using 4 colors just to make a point. And say I do that, and now this vertex over here has 3 different colored neighbors, so I guess I need a 4th color here. Okay, and so on. Yeah, you can see this particular graph is colorable with 3 colors too. So the delta plus 1 is seldom the best, but it's something that's always possible. And in some extreme cases, this is the best you can do. Okay, so if it's so trivial to color a graph with delta plus 1 colors, then why bother studying this as an algorithmic problem? So the thing is that we're in a streaming model, so we don't get to see the whole graph at once. The edges arrive one by one. And you'd like to use a sublinear amount of processing space. So you do not have enough space to store the graph or even a small fraction of it. So if the maximum degree is going to be delta, then n delta is the total number of edges, but you want to use little o of n delta space. Okay, so if you think about it, you can't really run the greedy algorithm, because one thing that the greedy algorithm has to do is to consider a vertex and say which color is free or which colors are free for this vertex. For this, I have to know what the neighbors of the vertex are. And if I've not stored that information, so if I have only this much, then for a typical vertex, I barely know I don't know even a constant fraction of who its neighbors are. So how can I possibly do this? It's not obvious at all. So you might wonder, is it even possible to do this? Is it even possible to produce a delta plus one coloring under a space constraint like that? Okay, so this is where a very interesting result comes in, and I have to tell you about this result. This result has nothing to do with robust algorithms, but it is important to our work. So I want to say a little more than just the result, and actually say something about how it's obtained. Okay, so let's consider what we have to output. We have to output a coloring, meaning we have to output a number between 1 and delta, say, for every vertex. So that's n log delta bits, just to specify what the coloring is. So the ideal space usage would be basically this, something like n log delta. If you think of log delta and log n as being of the same order, then n log n. So a space of the form n polylog n is fairly common in graph streaming, and it is the optimum space usage for various algorithms. So this space bound has a name. It's called semi-streaming. Okay, so the word semi-streaming just means space O tilde of n. Okay. Oops, not what I meant to do. Yeah, so you can see that term. Good. So there is a semi-streaming algorithm possible to produce a delta plus one coloring, and it uses this idea that the authors called Pellet sparsification. The authors in this case are Assadi-Chen-Khanna, and this work is a best paper awardee at SODA 2019. Really impressive paper. If you don't know it, I highly recommend seeing the details. Okay, so their algorithm is very simple to explain. So simple that this is what it is, basically. So they say at each vertex in the graph, we pick a random list of colors from our delta plus one sized palette. So we have to overall color with delta plus one colors. So let's say, here I pick these 3 colors at random, 3 colors at random, and so on. Okay, so let's say the list size is T. So I've picked T random colors at every vertex. Okay, so now I have a list LX per vertex X. And now the graph comes. So all of this work is done before I even see the input stream. So now the stream comes in. As each edge arrives, I say, do the 2 endpoints of this edge have a potential color in common? That is to say, do the lists intersect? So for example, if this edge over here were to come in, say this edge over here were to come in, I see that this color over here, this light gray color, is repeated here. So I'll say, okay, this edge is potentially dangerous, and I better remember that this edge was in the stream. On the other hand, this vertex's list and this vertex's list have nothing in common, so I can forget about this edge when it appears here. That is, if I have pre-decided that I will only color this vertex from this list and this vertex from this list. Okay, so I don't care whether this edge is there or not. There's just never going to be a conflict. Okay, so if you apply this idea throughout, then after a while you will find yourself storing only, I don't know, in this case, if this were the input graph, you would store that edge because there's an intersection between the lists. You would store that one. If I make a mistake here, someone please call out. I think you would store that and probably nothing else. Yep, I think the other edges are between vertices that don't conflict. Okay, so in general, you're going to store a hopefully small subset of all the edges, and this will help you attain your space bound. And it's really not very hard to compute the expected number of retained edges. It's a very straightforward probability calculation. So you're choosing lists of size T out of a palette of size delta plus one. So there are T squared opportunities for collision between 2 lists, and you're choosing from a universe of size delta plus one. So it's T squared over delta plus one. That's the probability that there is a single conflict between a pair of vertices. And so the expected number is n log squared n if you set T correctly. In this case, you set T to be order log n, and it works. Okay, so that's all very good. But now how do you actually produce a coloring? Okay. So what I'm saying here is that if you commit to using only the randomly chosen lists for each vertex, and then if you commit to giving each vertex a color that is from its list, then retaining these edges suffices to produce the coloring. But the trouble is maybe you restricted yourself too much, and it's not actually possible to color the vertices from these lists, even though it would have been possible to color with delta plus one colors. So this is not true, and this is the major theorem. So so this is why this is the best paper Best paper awardee. If it were just this, I don't think they would have won the award. But this is the major result. That it is actually possible with high probability using palettes of that size to complete a coloring. Okay. So for the purposes of this talk, we don't need to know how that works. We just need to know that there is this algorithm, and this is how you sparsify the palettes from delta plus 1 size to only log n size. Okay, finally, let's talk about robustness.
Before we
I
move
understand.
on, I
Yes,
have a quick question.
Yep.
So you did assume that delta is like kind of like log n.
No. I didn't assume delta is log n, right? So okay. So maybe are you saying at this final step over here? Okay, so
Yeah.
let's see what's going on. So number of edges in the graph is n delta. So you've canceled that.
Okay.
Delta cancels, and now we have n t squared, and t is log n, so it's n log squared n. Yeah.
Okay.
Yeah. Yeah. Okay. So this, as I understand, is the fourth talk in the series of robust algorithms. So maybe robust algorithms has been defined enough times by now that you've seen it, but just in case there's people who are coming to this talk who didn't come to the previous ones, let me just say what it is. So the basic thing in robust algorithms is that the outputs of a streaming algorithm might feed into the process that generates inputs for that algorithm. And you can imagine this happening, for example, if you're running a recommender system, for example, you have a stream of data saying that people have watched this movie, read that book, and so on and so forth, and you want to make recommendations. Now, based on your recommendations, people decide what to read next or what to watch next, and so that affects the rest of the stream that you see. So a whole bunch of algorithmic analysis that you might do under streaming will fail to work if the stream itself depends on the process that was used to analyze the stream. Yeah? Now, to make sure that your algorithm works despite potentially problematic dependence, so one way to do it is to say, let's imagine that the stream is actually generated by an adversary who is out to get you. So you've designed a streaming algorithm, and there's an adversary who says, now that this is the algorithm, I'm going to run your algorithm. I'm going to see what it outputs. And based on what you output, I will actually provide further tokens in the stream that will make the stream hard for you and cause you to make an error or use too much storage or something like that. Okay, so you can model this as a game between a space-bounded algorithm, which is just say computing some kind of sketch, and a powerful adversary who's computationally and space-wise unlimited. So the adversary provides the tokens that make up your stream. So it gives you a token, you sketch it, you produce a result. This algorithm is supposed to compute some function or the other. So whatever function is being computed is a result. So the adversary gets to see your result. And based on that, he says, aha, I know how to defeat you. And he gives you a next token, which makes it difficult for you. And then he keeps doing this until he finally breaks your algorithm. Right? So this is the game you're playing. And of course, as an algorithm designer, you want to design your sketches in such a way that the adversary is unable to defeat you. Okay. So, right. Let's look at how the adversary can defeat the algorithm we just saw for graph coloring. Okay, so let's take this algorithm, which we'll call palette spacification sketch, or PSS, and let's play it against the following adversary. Now the adversary has to give you a graph of maximum degree delta. So let's say we start with an initial graph whose maximum degree is somewhat less than delta, so the adversary has some room to add in more edges. Okay, so gives you this graph, you produce a coloring, and then based on this coloring, what can the adversary do? So this coloring gives you color classes. Each color class is an independent set, right? So this is the set of vertices colored 1, the set of vertices colored 2, and so on. Now, when this algorithm, think about how this algorithm chooses colors. It gives each vertex a list and then chooses the color from that list. So within a color class, it's guaranteed that so the same color was being used for all the vertices in that color class. So we're pretty sure that there was no edge there. So the coloring that it has produced is definitely valid, right? We can also be sure that the lists intersect, because for every vertex, in this class, the color 1 is in the list. It chose the color 1 from its list. So all these vertices have intersecting lists. So this means if I now introduce a new edge inside this color class, so between two vertices in this color class, then since those two vertices both have 1 in their list, the algorithm is going to store that edge. Okay? So that's its logic. Wherever the lists conflict, wherever the lists intersect, it stores the edge. So the adversary can now insert a whole bunch of edges, knowing that the algorithm will store all of them. And in this way, the algorithm, the adversary can force the algorithm to retain all subsequent edges that he introduces, causing the space usage to blow up to n delta. And so n delta is linear space. Okay? So we have failed to have sublinear space. Okay, so right. So definitely that algorithm doesn't work. So could a different algorithm work? If you try for a while and you fail, then you say, okay, so let's relax the problem. Instead of asking for a delta plus 1 coloring, which we know is combinatorially the best possible, how about a coloring that uses f of delta colors for some larger function f, like maybe delta squared colors? Okay, so delta plus 1 was too hard. Let's try delta squared. Okay, so we can indeed get something like this. So I will just outline some of the results that are relevant to this talk. And actually, over here are the results that I'll actually spend some time talking about. There's more, and maybe at the end of the talk, I'll say what more there is. Okay, so first, an upper bound. So using space sublinear, so note that this is n square root delta, linear space is n delta. So using some sublinear amount of space, it is possible to get a delta squared coloring. It's not semi-streaming space though, right? Because that would be n log n or n polylog n. But we can get down to semi-streaming space if we give up a little more on the colors. So if we use delta cube colors, then we can get down to semi-streaming space. Now there is a caveat to this algorithm, which is that it, well, we will see once we see what the algorithm is, that it requires a lot of random bits. And yeah, maybe I won't say more about this until we have described the algorithm. But this caveat can be removed. This is a more recent result. This is joint work with, okay, I should say the earlier work is joint with Pranthar Ghosh, who's in the audience here, and Manuel Stockel, another student of mine. And in more recent joint work with Pranthar and Manuel, and also Safar Assadi, we've shown that you don't actually need the oracle, you can remove it. And that's nice. I hope to at least outline that algorithm today. We've also shown that you can reduce this tree to a 2.5, but I won't go into that. Okay. How good are these results? Remember, we started out by having a delta plus 1 coloring in the case of just plain old semi-streaming, not adversarially robust algorithms. But now, we are at delta squared, delta cube, and so on and so forth. It turns out that there is a lower bound saying that if you want to run in semi-streaming space, then you actually must spend almost delta squared colors. So you can't do the thing that Palette's classification sketch would have done. So you cannot get a delta plus 1 coloring. You cannot even get order delta. You really have to spend delta squared. A different way of looking at the lower bound is that if you wanted to produce a coloring using about delta colors, so like order delta colors, then there's no sublinear solution possible. You have to basically store the whole graph. So n delta space is required. These are special cases of a more general trade-off that I'll get to. Okay, so that's as far as results go. Let's make a couple of observations before we get into any proofs. So this talk is pretty much focusing on randomized algorithms. And if you haven't seen robustness much before, then it may not be immediately obvious, but if you think for a while, you will see that it's not so hard. Any deterministic algorithm is automatically robust because the guarantees of a deterministic algorithm are, worst case, that no matter what the input is, it never makes a mistake. Therefore, an adversary basically knows exactly what's coming. He knows how a deterministic algorithm is going to behave for a given stream. So he can predict all future operations, and he can design his entire bad input before even actually running the algorithm. So he gets nothing out of actually running the algorithm. An all-powerful adversary can run it all himself, right? He knows what your deterministic algorithm will do. So there's nothing to do. Such an algorithm is already robust. Okay. Now, in streaming, you might know that many problems do not admit a deterministic algorithm nearly as good as a randomized algorithm. Typically, you need randomization to get interesting results. So, since your algorithm is randomized, now the adversary has something that he can do with you, right? He can actually try to exploit your algorithm's outputs to learn about the hidden random state of your algorithm. So if he can learn about your random state, then he can design inputs that presumably defeat whatever it is this randomized algorithm was doing, and can sort of get you back into a situation which is more like deterministic, which is hard for the streaming algorithm. This is just a high-level thought. Okay? But it's a useful guiding principle for algorithm design. So in order to design a robust algorithm, the thing you should focus on is hiding your random state from the adversary. Okay. I'll also mention that recently it's been of interest, especially in the complexity community, to consider something called pseudo-deterministic algorithms. So this can be done in various computational models. You can also do it for streaming. So a pseudo-deterministic algorithm is a randomized algorithm that has the property that with very high probability, it will give a fixed answer for every given input. So there may be multiple correct answers, and in general, a randomized algorithm could pick among these many correct answers. But a pseudo-deterministic one behaves sort of like a deterministic one in the sense that there is one fixed answer which occurs with very high probability. Okay, and any such algorithm is also automatically robust for much the same reason as deterministic ones are. Basically, the adversary gets no information out of running your algorithm because it's with high probability going to give you that fixed answer. Okay, all right. So let's talk about at least a couple of algorithms. So I've already mentioned one best paper awardee earlier in the talk. Here's another best paper awardee. So result stands on the shoulder of two best paper awards. So this by Ben Eliezer, Jairam, Woodruff, and Yogev introduced something that they call a sketch switching technique. And it provides a general framework for converting any existing streaming algorithm into a robust streaming algorithm. So what they do is they say you have some existing algorithm A for some problem. Let's run lambda copies of this algorithm, independent copies in parallel. Right? And let's maintain the most recently reported result that we gave. Okay. And we also maintain a single variable which keeps track of which of these parallel copies of A is currently being used. So there's a sense in which we will say that we'll be running these copies of the algorithm in parallel. After some time, we're going to say, oh, this algorithm is no good anymore. I'm going to discard it. Okay, this one's no good anymore. I'm going to discard it. And this is my current copy of the algorithm. So I'll be reporting results from this copy of the algorithm. Okay, I'll also be running these other copies of the algorithm, but I'll keep their results hidden. Okay, so that the adversary doesn't know anything about these. Okay, so each time I receive a token in the input stream, I'm going to process that token, of course, in all of these sketches. So this one, and this one. And then I'll check, has the stream changed so much that my most recently reported result is not valid anymore? Okay, so maybe the function that I'm computing has changed a lot and I have to actually report a new result. If I don't have to do that, then I say, you know what, life is good. I just stick with the previous result. So the adversary gets no new information because he's just getting the same result that he got before. But if the result has to be changed, then I say, okay, I will report the new result and I will discard the sketch that led to this new result. So from now on, this sketch is not going to be used. Any future results will come only from these other sketches about which the adversary has no information. So you can see already, it's kind of intuitive that an algorithm designed this way is going to be robust. So what is the cost of doing this robustification? Basically, we have blown up the space usage by a factor of lambda. So this works provided the function that we are computing has the nice property that it won't change too much over the lifetime of the stream. Now, for many interesting functions like estimating norms, which is sort of a bread and butter thing in data streaming, it is the case that you can come up with a nice bound on this number, which they call the flip number. So if a problem has a small flip number, then this general technique shows that you can robustify an algorithm for it. Okay. So why am I saying all this? So we're going to use this technique in our own algorithm, but we can't use the technique just as is, because for one thing, so this technique was developed, I guess, with problems like this in mind. You're estimating the norm of a stream. So you're computing some real number. Okay? Now, what we have to compute is a coloring. It's nothing like computing a real number. And actually, the adversary can cause your coloring to become invalid with every new edge that he has. So every time you see a token, the edge could be between two vertices that were colored the same, and therefore you have to change your coloring. So we can't be discarding a sketch with every edge that comes in. So we have to do something better. Okay, so that gets us to algorithm 1. So here we're going to do sketch switching, but we're going to do an additional buffering technique on top of that, or chunking technique. So imagine that our graph, which consists of n delta edges with maximum degrees delta, is split into chunks of size n square root delta. So there's square root delta chunks in total. So what I'm going to do is run several copies of this Assadi-Chen-Khanna palette specification sketch in parallel. Each time I get to the end of a chunk, I'm going to discard that particular copy of the sketch and just retain the rest, right? So the sketch 1 processes only this chunk, sketch 2 processes the first 2 chunks, and so on and so forth. Okay, so now how do I produce a coloring? So suppose we are somewhere here in the middle of a chunk, and I have to produce a coloring for the current graph. So I will look at the palette specification sketch for, well, so my variable cur refers to the most recently completed chunk, I guess. Maybe I should have called it cur -1. But this portion of the graph, which has been previously processed and just processed using this palette specification sketch, that's going to give me a certain delta +1 coloring, right? Using the Assadi-Chen-Khanna algorithm. So I have that coloring, I call it col1. Separately, this portion of the graph, I have completely in my buffer. Okay, so I'll store them. It's of size n square root delta, so I'll say I can afford this because I'm shooting for n square root delta amount of space. So this part of the graph is completely stored, and I can just do a greedy offline coloring for it using, again, delta +1 colors. And then I can just take the direct product of these two colors. So give each graph a color, which is the Cartesian product. It's like a tuple consisting of color obtained by this coloring and color obtained by that coloring. And then this works. So this makes sure that no edges from the current chunk will conflict, and then no edges from the earlier chunk will conflict because of the correctness of the PSS algorithm. So overall, we've got a delta squared coloring, and we have spent n root delta space. So it is possible to generalize this to use even less space, but at the cost of increasing the number of colors. I see I have a typo there. And one good thing is that it's possible to fix these typos live. Okay. Okay, so this should be delta to the k. There's also another extension possible, which is that this algorithm, as described, only handles insert-only graph streams, and if edges can be deleted, then it doesn't work as stated, but a variant of this can also handle edge deletions. Okay, so it's more than just a variant. One has to do quite a bit of additional work, but the basic idea of using chunks and then taking the product of colorings remains. Okay, so good. So for this talk, I won't say more. Yes.
Quick question. So with edge deletions, like the coloring shouldn't really change, right? Like what makes it?
Okay, good. Yes, thank you for that question. So when you delete an edge, of course, the coloring remains valid, but the problem is the maximum degree might drop. And so if you want to stay within the bound of delta squared colors, at some point you may need to recolor.
Okay.
Yeah.
And each of these sketches that you're maintaining, they are like fresh randomness, right? Like.
Yeah, yes, they're right. So there's a separate amount of randomness used in each of these. Yeah.
So it's totally different from, like, let's say if I have an algorithm that after like every result, I change my list of colors. Like I add some more colors or I drop a few colors just to preserve this hereditary kind of property that my coloring still remains valid with the edges that I preserve. So that algorithm would be trivially bad, would it be?
Sorry, I don't think I understood the proposed algorithm.
So here's my algorithm. So I have these lists, like the Assadi and Sanjeev-Khanna paper. So I have these list of colors. So after every time, if the adversary gives me an edge, what I do is I modify my list by, let's say, one color. So I either add a new color to every vertex, or I remove one color from every vertex that I have in my list. So I just pick a random color in the list. I just take it off.
So yeah, in some sense, the algorithm that I'm about to show next is kind of like that.
Okay.
You have to be a bit more careful with how big these lists are so that everything works.
Okay.
Okay. Yeah. Okay. Good. So let's see that maybe. Right. So I guess Venkata was proposing to make some changes to the pellet specification algorithm, and that's kind of what this algorithm is. So I like to think of this as multi-level pellet specification. The idea being that, yes, you choose random pellets, but you do this in multiple levels. So in some sense, there's a level 1 list, a level 2 list, all the way up to a level delta list for each vertex. So this delta is the maximum degree. So each time a vertex's degree changes, I'm going to skip whatever level I was at. I'm sort of going to go to the next level, right? So I'm going to be choosing colors for each vertex from the level corresponding to its current degree. Make sense? Okay, so let's see. So this algorithm is going to, first of all, just use randomness to generate a bunch of lists like this. So this part, again, is not input dependent. So then the stream starts coming in. And what I have to store is edges that possibly conflict. Okay, so the set of dangerous edges which conflict for basically the same reason as the Assadi-Chen-Khanna algorithm. The only thing is now I don't know in advance which particular levels palettes I will be using for a vertex, right? Because it depends on what its degree turns out to be at a future point in the stream. So I'm just going to take a very conservative approach and say, so if I look at the current degree and let's say it's 5, I'll say at all levels 5 and higher, if there's a conflict, then I will say that, okay, this edge is dangerous and I'll store it. Okay, so let D be the set of all dangerous edges that might cause some future conflict. So I'll store all of them. And the basic operation of the algorithm will be like this. So whenever an edge comes in, first of all, we keep track of the degrees. So we increment the degrees of the vertices. And for every level that is greater than or equal to the larger of the 2 degrees, I store the edge if there's a conflict. Yeah, so this is the same logic as in the PSS algorithm. The lists intersect, I store the edge. Now, I also recolor the vertex U. And U, I will say, it's arbitrary. Okay, it doesn't have to be the larger degree vertex or anything. Just pick one of these 2 arbitrarily and recolor it. Okay, so let's say we recolor the vertex U. Now, what does it mean to recolor the vertex U? So we'll look at the current degree of U. And as I said, we'll be trying colors from that particular level. So if D is over here, say, so if D is over here, then I'll be choosing colors from LDU. I go about looking in the dangerous edges to see what colors have already been used by the neighbors of U. Okay, so I want to recolor the vertex U. So I look at every neighbor of U that has been recorded in D. So everywhere there is a dangerous edge. The set of colors used by these vertices is certainly not available for U, right? So long as I give you a color different from this used set, I'm good. Okay, so now I'm going to walk this list, the Dth level list, one by one, and try each color until I find one that's not been used. Okay, and note that the colors are ordered pairs. So a color is of the form D comma X, where D is the degree, current degree of the vertex, and X is from that list. Okay. So the only possible conflicts are, if this is a vertex of degree D, the only possible conflicts right now are another vertex of degree D. Okay. Okay, so this the space of colors used is, so D can take one of delta values, that's a degree, and X comes from a palette of size 2 delta squared, because, well, that's what it is. We've chosen the lists out of a palette of size 2 delta squared. Why delta squared? Why not just delta? Well, we'll see. So that comes up in the analysis. Okay, so yeah, judging by the time, I think this is the only analysis that I will actually show. There's another one I had written up, but I think I'll skip it. So let's look at, for every edge, the probability that there is a conflict at some level. Okay, when you do this algorithm. So that's the same thing as saying, just take the sum, I equals 1 up to, should be delta, I equals 1 to delta of probability that the conflict happens at the ith level. Okay, so what's the probability of a conflict? it's the length of the list squared over the size of the universe from which you drew the random colors. So once again, if you're choosing a list of length t, then there are t squared opportunities for a collision. So and each collision probability is 1 over 2 delta squared. So it's t squared over 2. After canceling 1 delta, you get t squared over 2 delta. Okay, that's the probability of a conflict at some level. So the expected number of edges that you have to store, these dangerous edges, is, well, total number of edges in the graph times this probability. And so after canceling the delta, once again, we get nt squared. And we want this to be semi-streaming. So we want this to be O tilde n. So just pick t to be something times log n, and that will do. So that'll make it semi-streaming. Okay, now why is this choice of t equals log n good? For this, we have to consider when might this algorithm fail. Okay, so let's briefly look at the logic again. Where is the potential failure point for this algorithm? The failure point is right there. So over here, when we're trying to recolor the vertex, we have said these colors are used, and try each color until we find one that's not in use. Maybe we don't find such a color. Maybe we finish the whole list and all the colors have been used. That's a failure. And so we fail to recolor you, and then the algorithm is just going to crash at this point. Okay. Right. So the probability that the list from which you're trying out colors is completely inside the used set is basically, it's by independence, it's the product of the probability that the jth element is in the used set. Okay, what's the probability that the jth element is in the used set? Well, how big is the used set? The used set consists of all the colors used by all the neighbors of this vertex. So just sum over all neighbors. This is just a union bound. Sum over all the neighbors and look at the probability that the jth element of this list was used as the current color by the neighbor. Okay. Now, since the jth element of the list is just a random choice from a universe of size 2 delta squared, this probability is 1 over 2 delta squared. The sum is over all the neighbors of u. The maximum degree is delta, so there are at most delta terms in the sum. Therefore, this is delta over 2 delta squared. And then after some calculation, this is half to the t equals log n, so you get 1 over poly n. Okay, so we have shown that there's only a 1 over poly n probability that you fail when you try to recolor a vertex. And over the lifetime of the stream, there are, let's say, at most n squared edges. So the probability that you will fail at some point is at most 1 over n squared. Okay, so this algorithm works with high probability. Okay, finally, why is this algorithm robust? So for this, you have to look at, so what could cause it to be not robust? So the adversary can't really make you fail, right? We've already argued that the probability of failing is small. So where is the failure mode of this robustness? So you see, we did say that we want to, right. So we want to keep our space usage as O tilde n. And we've computed here that the expected number of edges stored is O tilde n. We have to turn this into a high probability result. And we say that it's never going to be the case that we have to store more than this. So for this, you just have to note that the random coins that affect whether or not you store an edge in D are completely independent of the random coins that affect the coloring that you output. Okay, so how do you decide to store an edge in D? It's based on if certain lists intersect, right? And these lists are at levels degree to everything higher, okay? Now, as far as the coloring was concerned, what random variables were used to produce the current coloring? So the current coloring, it's done over here, right? We're doing this recoloring. So the next time we store something in D, the degree will have increased, okay? And so the recoloring was done using the current degree, and storage of an edge in the set capital D will be done using future levels higher than the current degree. So those are independent of the randomness used to do the recoloring. Okay, so the argument is a little bit subtle, admittedly, and it's a bit hand wavy when I say it like this. And it does take about a page of carefully looking at random variables to make sure that everything is correct, but it works. You can basically make the argument that the adversary learns nothing and he can do no worse than an oblivious adversary that just picks a bad input in advance. Okay. So let me move on to just talking briefly about what to do about this randomness cost. So the algorithm that I just showed you had, well, let's look at this picture maybe. Yeah. So this algorithm has one unfortunate feature, which, because I guess I talked too fast, you may not even have noticed. You have to choose a lot of random colors at each vertex. So how many do you have to choose? There's lists. Well, lists of length t is log n. That part is fine, but the number of such lists is delta, right? So there's delta levels of lists. So there's delta amount of information to be stored at each vertex at least. So that's already n delta. And that looks bad. I thought n delta is linear space. So what's going on? How is this even a streaming algorithm? So then, and I have to say, okay, so what's going on here is that this is just pure randomness. It's not really storage in the sense that this is not information about the input. This is just a bunch of random bits. So the way I would address that criticism is to say that if you had random bits available somewhere as like read-only memory and or hardware or what have you, you can just consult these random bits anytime to make your decisions, and it's not input dependent. So right now, whether you want to count this as storage or not, it can be debated. Okay, so I guess I'm proposing that we don't count this as storage so that we can still refer to this as a sublinear space algorithm. And you may not like that, and there's a way to answer this, and that's what this is about. So it turns out that instead of storing actual lists of colors, what one can do is pick a hash function with sufficient independence. 4-wise independence turns out to work, and just store a hash function at every, so store a few hash functions, say a list of hash functions. Rather than a list of colors, I have a list of hash functions for every level. Now, these levels no longer refer to degrees, by the way. So I'm using the same yeah, sorry, I lost track of something here. Okay, yeah, right. So these levels now correspond to n-sized chunks of the input stream. So the input stream has n delta edges in it. So I'll chunk things into, okay, so this shouldn't be n delta edges, sorry. So this is n edges. Sorry, this is just n edges this time, n edges. Okay, so each chunk has n edges, and so there's delta total chunks, and these deltas over here. So this delta refers to, well, yes, it's still maximum degree, but it refers to the number of chunks, so the chunk number, rather than looking at the current degree of the vertex. Okay, so the way I've reduced space is right, sorry, well, right, yes, good. So the way I reduce space is that I have just this one storage that I need overall. So rather than storing a bunch of lists per vertex, I'm just storing an overall list of hash functions. And then these other sets D of dangerous edges, again, which are edges that can cause potential conflict. So now in order to color a vertex, rather than picking a color from a random list, I'm simply going to evaluate a hash function at that vertex, and it's going to spit out a color in the range 1 up to delta squared. Okay, so all this is saying is reduce the pure randomness of choosing a purely random color to choosing something that's pseudo-random. So you have a hash function that sort of introduces dependence between the colors of the vertices, and then you reduce the space usage from n delta to only sort of this table overall. So it's t delta for a suitable value of t, which will again turn out to be log n. So the dangerous edges, I guess the logic for the dangerous edges, let me see how much of this I have time to go into. So I certainly don't want to do the analysis considering the time. So so let me just say that you right, okay. So treat this the hash function as I said, as a coloring for every vertex. So h of v is the color for v. According to this hash function, if two vertices could possibly get the same color, then any edge between them is considered dangerous, and it's stored in the set dij. Okay, so that's the logic for the dij. And then after this, there is some amount of Chebyshev type analysis to say that these DIJs won't get too large, and we'll enforce that they don't get too large by saying if it's about to get too large, then we will simply purge this DIJ and we'll say it's not valid anymore. When it's time to recolor a vertex, or when it's time to color a vertex rather, we're going to produce two different colors. So one is a coloring using all the dangerous edges that we've stored and the current chunk, which we're storing explicitly. And the second is using the hash function. So by our logic, we know that if the hash function doesn't provide if the hash function has a collision, then the edge would have been stored in the dangerous part. So either the hash function itself gives you a good coloring, or else this other thing gives you a good coloring. So if you take the product of the two, you have an overall good coloring. So the rest is kind of like before, but with a slightly more complicated analysis that I shall skip. So let me skip past that. And I do want to spend at least a few minutes talking about lower bounds. Did anybody have a quick remark, question, anything like that they wanted to get out of their system? Yeah, because if not, I'm going to switch gears. If I lost you, then this is a good place to wake up again, because this is completely different from what went before. Okay. Right. So my children say that all my talks have Alice and Bob in them. So yes, here's the obligatory Alice Bob slide. So lower bounds in data streaming are pretty much standardly proven using the following setup. You set up a communication game between two players, Alice and Bob. Alice has a prefix of the stream, Bob has the rest of the stream, and then the streaming algorithm gives us a communication protocol for something interesting. Okay, so here things are slightly different. Instead of Alice and Bob each having an input, only Alice will have an input, and Bob will produce output that has some information about Alice's input. Okay, so we're going to simulate here a robust streaming algorithm for something or the other, in this case, coloring. Eventually, it'll be coloring. So Alice gets an input which she thinks of as a prefix of some stream. She sketches it and sends over the sketch to Bob. Okay, that's the communication. It's one-way communication. Now, at Bob's end, he runs the query portion of this streaming algorithm to extract some results from the sketch. Okay, and let's say writes down the result. Okay, so this is part of Bob's output. Now, based on the information that he extracted, he says, okay, I'm going to continue the stream as follows by providing the following, adversarially bad tokens to continue the stream. Then I'll sketch it some more, and I'll run another query, and I'll get some more information. Okay, and then I'll do it again. I'll just do it a few times. Okay, so after several runs of these, we've hopefully extracted plenty of information about that initial input. So really, I want to say that a lower bound for robust streaming algorithms follows because it allows a communication protocol of the following shape, that Bob gets a certain message about Alice's input X, and using this, he extracts Y, which is some plenty of information about X. And then you want to say that for basic information theoretic reasons, this is not possible, and so you have to have a lot of communication. Okay, so the specific communication game that gives us our lower bounds is something that we call the subset avoidance game, or just avoid for short. So in this game, Alice has an input set from the universe of elements 1 up to T. Alice's set is of size A. She sends a message to Bob, who now has some partial information about this set. And his goal is to produce a new set, which should be completely disjoint from Alice's set and should have B elements in it. Okay, so A and B are specified parameters of the problem. The universe size is T, A is Alice's set, B is the desired output set size from Bob. So we can prove this is kind of a new problem in communication complexity. Fortunately, it's not a terribly hard problem to analyze. One can prove that the one-way communication cost of this problem is omega AB divided by T. And well, minus a little term depending on the error. So we actually need an extension of this game to do the streaming lower bounds. We need a direct sum version of this game. So Alice actually gets k different sets, each of size A, and Bob has to output k different sets, each of size B, and then they must all be, each AI must be disjoint from the corresponding BI. And one can generalize this bound to show that this game requires communication cost KAB over T. So I should point out that although we don't need this for any streaming purposes, there is a converse theorem which says that this bound is really tight. Even with just deterministic communication, you can achieve this bound of AB over T. Yeah. And of course, that means you can achieve KAB over T for the direct sum case. Okay. So here's why this thing is relevant for graph coloring. So let's say that we have a robust K coloring algorithm, okay, for graphs. Now, what we want to do is we want to solve this avoid problem, right, where Alice has a set and Bob has to spit out a disjoint set. So let's take Alice's input set and convert it into a graph. And we'll do this in kind of the most simple way you can imagine. Take enough vertices so that the universe of size T will fit into the space of edges of this graph. So if you take n vertices, there are order n squared edges possible between the vertices, and just take a random mapping from this universe to the space of edges. All right, so just do that at random. Now, if you do things at random, that means with high probability, all the degrees will be kind of what they should be. Yeah, if everything were completely, everything were exactly balanced. Yeah, that's just a Chernoff argument. So the rest of the argument assumes that that's happened and all the degrees work out roughly the same. Now we feed this into our robust coloring algorithm, which is going to give us a coloring. So it's going to split the vertices into color classes. Now inside each color class, Bob knows that Alice did not have an edge. Okay, so the edges of this graph are, remember, the elements of Alice's original set. And Bob's goal is to produce a subset that avoids Alice's set. So in some sense, he wants to find out where there are missing edges in this graph. So he knows that all these edges are missing. The edges inside each color class are definitely missing. So Bob can go ahead and add all such edges, but he shouldn't add all such edges because that does something bad. See, this algorithm only works for graphs of maximum degree delta. So Bob doesn't want to do anything that will hurt the maximum degree by too much. So he does the least damaging thing possible and adds only a matching inside each color class. So by adding only a matching, you ensure that the degrees go up by at most 1. Okay. And also, you've also got almost as many edges as there are vertices. Maybe you're missing one vertex from each color class because it's of odd size. Okay, but then you can go ahead and add these matchings. So add these matchings, you have now a slightly larger graph. Repeat, you get a new coloring, do this again, just keep doing this. So in this way, you extract lots of edges that Alice definitely did not have in her graph. And so Bob is able to output a large subset disjoint from Alice's set. So if you now plug in the parameters, then you see that you can start with an initial maximum degree being, say, epsilon times n for some small constant epsilon. That is, if the parameter a here is epsilon times t. So by the way, I should note that on this slide, each occurrence of epsilon is possibly a different constant. Yeah. So now you take this whole, you repeat this whole loop epsilon n times. So you get epsilon n matchings. The size of each matching is n minus the number of color classes. Like I said, at most one vertex per color class is unmatched. So roughly you get epsilon n squared edges overall that have managed to completely avoid Alice's set. So you've solved the avoid problem with a universe of size n squared and a and b being of size epsilon n squared. And so if you plug into the lower bound, this gives us a lower bound of omega n squared. So we've just concluded that a robust algorithm that produces order delta colorings needs n squared space. Yeah. Okay, so n squared space, well, it's really n delta space. The graph that I created happens to have delta equals order n, so that's why it was n squared. So I only stated a special case of the more general theorem. The most general version that we could prove says if you have a robust K coloring algorithm that works up to maximum degree delta, then you do a reduction from avoid K. Sorry, this K is not the same as that K. This is little K, is capital K. And then you get a space lower bound that looks like this, n delta squared over K. So that's the general trade-off. And the two interesting points on this trade-off that I mentioned at the beginning of the talk were, if you want a coloring with order delta colors, which is close to the combinatorial optimum of delta plus 1, then you need linear space. So no sublinear space is possible. And that's one way to look at it. Another way to look at it is that if you want to run in semi-streaming space, then you have to spend at least delta squared colors, roughly, up to a log factor. Okay, so this is nice. remember that every deterministic algorithm is automatically robust. So this result actually gives you a separation between deterministic and randomized algorithm. So for randomized algorithms, we have the palette specification sketch, which says delta plus 1 colors is achievable, but deterministically, you need delta squared colors. So actually, independent of our work, Assadi-Chen and Sun showed that deterministically, you actually need even more than delta squared. You need exponential in delta colors. So there's a trichotomy now. So randomized is delta plus 1, robust is delta squared, and deterministic is exponential delta. It's kind of nice. Okay, so in closing, I'll mention just one other thing. So my student Manuel has sort of taken this line of work considerably deeper. And among other things, he's been looking at this problem called missing item finding, arguably even more basic problem than graph coloring. And it gives you some nice separations. Like here we have a separation between deterministic, randomized, and robust. So he gets deterministic, randomized, pseudo-deterministic, various flavors of randomization, like oracle randomness versus not oracle randomness, and so on and so forth. So check out his work in SODA 2023. Good. So I think the time is right to stop and say thank you. So I will do that. Thanks, guys.
Thank you very much. Yeah, that was a really nice talk. I enjoyed it. Any questions? Well, if you have time,
Sure.
So in the algorithm, so the dangerous edges that you're maintaining, like I'm assuming like the problem arises when you change the list of your random colors and there was an edge which was probably should have been stored but wasn't stored, right? So something like suppose
no, this never happens. We are anywhere there's a potential. Okay, good. So the logic for storing an edge ensures that anytime it might be the case that this vertex and that vertex could get the same color, that edge will be stored.
Yeah, but since the list is changing, those potential edges will also change, right? So like if the list changes, then
no, we're considering all future lists that may occur.
Oh, okay.
For each level I, from the current degree all the way to delta, we're going to store it if there's a conflict at that level.
Okay. Yeah, that makes sense.
Yeah, so the way the adversary can try to hurt you is kind of similar to what we were doing back here. Where were we? Yeah, back here where we said just try to insert edges that always cause you to store the edge that is being inserted.
Mm-hmm.
So the adversary can say, I'll give you edges only that are within the same color class, and then you will have to store this edge. Mm-hmm. So we've got over that particular problem here.
Okay. Yeah.
Yeah. So just because we are in the same color class doesn't mean that future lists will also intersect. So maybe future lists don't intersect. Yeah, it's fine.
Okay.
You may not necessarily have to store.
Mm-hmm. Yeah, that clarifies. Right. If there are no other questions, or maybe I can just like stop the recording in case there are any more questions, people who are shy.